Hi everyone, today we are going to cover chapter 7, Geometrical Optics. In this chapter, we have three subtopics: 7.1, Reflection at a spherical surface; 7.2, Refraction at a spherical surface; and 7.3, Thin lenses. So let's have a look at 7.1 first. 7.1, Reflection at a spherical surface. When we are learning about reflection, we are talking about spherical mirror. We have two types of spherical mirror. The first one is concave mirror, which is converging mirror. And another one is convex mirror, which is also known as diverging mirror. So this is how the concave mirror looks like, and then this is how the convex mirror. So when we're drawing the mirror, we must include the small tiny lines along the mirror. And then the center line is called the optical axis. So in the spherical mirror, we have an imaginary circle, and at the middle we have the center point. Okay, and then in between the vertex and the center we have focal point. Okay, same goes with the convex mirror, where the imaginary circle is on the other side, and then at the middle we have the center, and then in between the center and the vertex we have the focal point. So let's draw again C and F for both mirror. Okay, so now we are doing the ray diagram. So let's say we have an object at the distance greater than the radius of curvature or center. So the first ray is go straight, and then you reflect it, go through the focal point. So that was our first ray. And then for the second ray, so you go straight through the focal point. Let's use orange. Go straight to the focal point, and then you reflect when you see the mirror, and then it goes to the parallel line. So this is our second ray. And then for the third ray, let's use pink. It will go straight to the center point, and then it will reflect it at the same point. And then this is our third ray. So when these three lines intersecting, there was your image will form. So this is where your image will form. So for convex mirror, at any position, it will yield the same image. So I'll just put our object here, and then for the first ray, it will go straight at the mirror, and then since this is diverging mirror, so it will diverge when you see mirrors. But where it will diverge? Is it here, here, or here? We don't know. So how we want to know where it was reflected? So let's use the focal point as the reference point. Okay, so we are drawing the reflecting rays. Okay, and then we need to extrapolate behind the mirror as a dotted line. So this is our first ray. And our second ray, we just go straight to the focal point, and then behind the mirror we need to use dotted line, and then in front of the mirror we need to reflect the ray parallelly. Okay, we're not done yet. We need to extrapolate more at the back because it's not intersecting with the first ray. So extrapolate more to see where it was intersecting. Okay, and then the third ray, we just go straight to the center. Same with the concave mirror just now. Okay, right, so where these three lines intersecting, there was your image will form. So this is where. Okay, let's look at the characteristic for the concave mirror. It was real image, it was inverted, it was diminished, means smaller in size compared to the object, and it was formed at the center, between the center and the focal point. For convex mirror, the image produced is virtual because at the back of the mirror was upright. It is also diminished, which is smaller in size, and it was formed at the back of the mirror. Well, actually, we have 5 different cases for concave and 1 for convex. So the first one we did just now. Okay, when the object is greater than the radius, go straight and then reflect at focal point, and then go straight and then reflect parallel line with the optical axis. So where the intersecting lines, there was an image. Okay, we've done this before. Okay, for the second case, when the u or the object distance is equal to the center point. Okay, and then the first ray goes straight and then reflect at focal point, and then the second ray goes straight to the focal point and then reflect in parallel lines with the optical axis. So the intersecting lines is your image form. So it was real, inverted, same size, and form at C. The third case is when your object is in between C and F. The first ray goes straight and then reflect at F, and then the second ray go to the focal point and then reflect it in parallel, and this is your image. It was real, inverted, magnified, and formed at a greater distance of C. The fourth case, when your object is on the focal point, so the first ray goes straight again and then reflected and go through the focal point, and then we don't have the second ray and we go using the third ray, so it was reflected to the center point and it was real or virtual and formed at infinity. And the last case, when your object is less than the focal point, the focal length. So this is your object, and then the first ray goes straight and then reflected at focal length, and then we don't have the second ray as well. With the third ray, okay, it goes straight and then reflected at center. Okay, and then this is our image. It was virtual, upright, magnified, and formed at the back of the mirror. So for convex mirror, we have just one cases, and it doesn't matter where the position of the object, it will yield the same image. So go straight, and then you will diverge the ray at focal point as our reference, and then second ray go straight to the focal point and then reflect it in parallel, and then you extrapolate this, and then the intersecting lines is your image. And it was virtual. Oh yeah, don't forget to use broken line behind the mirror. The characteristic is virtual, it was upright, it was diminished, and it was formed at the back of the mirror. Okay, next one, we are going to go through the calculation. So spherical mirror equation is 1 over focal length is equal to 1 over object distance plus 1 over image distance. Alright, and another equation is magnification. So M is the magnification is equals to negative image distance over object distance equal to height of image over height of object. Okay, so this is the sign convention table. This is very important. Okay, so you need to bear in mind that if you get your sign wrong, so your answer will be wrong. Okay, so I want to emphasize the last three. Okay, for the image distance V, the real image represent the positive sign, and then negative is virtual image, and then the focal length, positive for concave mirror and then negative for convex mirror. And then the magnifications, your image will be upright when positive, and then your image is inverted when your M is negative. Okay, next let's do some example. Okay, a pill bottle 3 cm tall, so that was your height of object, and then it's placed 12 cm in front of a mirror. So this is our object distance, U is equal to 12 cm. A 9 cm tall upright image is formed. So this is our height of image, 9 cm. Okay, the first questions, what is the mirror? The mirror is convex or concave, and why? So in order for us to know whether this is convex or concave mirror, we need to know the focal length value. So we are using the spherical mirror equations, 1 over focal length over 1 over u plus 1 over v. We substituting the value, and we don't have the v, so we are finding v in a separate place. So we are using the second equations. Magnifications is equal to height of image over height of object is equal to distance of image over distance of object. We have everything already. Just substituting all the values, and then at the end you will get the value of v is negative 36 centimeter. So we are substituting in the previous equations. Don't forget the negative, yeah? It will affect your answer. And then do your maths, and then you will get 18 cm. Okay, so how we know whether this is convex or concave? We look at the sign. So we have the positive sign. That means this is concave mirror. Refer to the table just now. So this is concave mirror because the focal length value is positive. Okay, next question is, what is the radius of curvature? So if you remember just now, spherical mirror is actually a imaginary circle. We have center and focal point in between. So we have the focal point already just now. Basically, the radius of curvature is just twice the amount of focal length. So we just times 2, and then you will get 36 centimeter. That's it.